All right, so last time we actually did an exercise. This was the exercise in linear regression. So just a quick review, what we're doing is that if we have a bunch of data, okay, so these are my data points, x1, y1, x2, y2, x3, y3, and so forth. I might have n points. I'm trying to fit a line that is sort of the best positioned not to be very far from all of those points. And the way we quantify that is by taking a sum between actual measured value yi for every point and the prediction of this linear model. And linear model is in the form of y is equal to a0 plus a1x. So that is my functional description of a line. And I'm looking for a0 and a1. Okay? So when I basically look at the difference between my measured value and what my model should be, I take a square of it. Okay? So I have this positive sum, and what we're really trying to do is we're trying to minimize this sum. Okay? So it's also often called least squares, sum of least squares, residuals that I'm trying to minimize. In the process of minimizing this sum, okay, I'm basically, what I know is true for the minimum, yes. Oh, sure. I was about to switch to MATLAB, so that's why I kept it. Sorry, I'll do this. So basically, this is my sum. Okay, this is my model, minus a0 minus a1 xi. So this is the modeled value. This is the measured value. I'm looking at the differences and squaring them. So this is one big positive sum. And if I'm looking for the minimum, what has to be true is that partial derivatives of this sum with respect to a0 and a1 have to be 0 for a0 and a1 that minimize it. Now, again, remember that xi, yi are actual numbers, so they're not variables here. The variables I'm looking for are a0 and a1. So when we actually do this procedure, and we did that on that worksheet in a simple case, basically you set the partial derivatives to 0, and you find basically linear equations in a0 and a1. When you clean them up for n points, you're going to get something like n times a0 plus this sum of all xi's times a1 is equal to y1, sum of all yi's. And similarly, second equation, again, my unknowns are a0 and a1. And then I can solve for those. Now this is a 2x2 system, so for 2x2 system, I actually have ready to go formulas. And one I gave you on the spreadsheet, which is Kramer's rule. It actually gives that this is what a0 and a1 should look like. And last time what we did is we did this exercise where here's a bunch of points, x and y. So this is my x1, y1, x2, y2, and so forth. And we created a linear regression function that takes these vectors as input and gives prediction of this a0 and a1 as an output. And I said you can use some function to compute these. So let's look at that code quickly. So start the MATLAB. So did everybody get to that code or close to finishing it? Because you will have to continue it and submit it by tonight as a quiz grade. So please work on it. So this is my code that takes x and y. N is number of elements, for instance, in x. And I can just say one of those sums is just sum of x's, sum of all x's. Sum of y's, sum of x. The sum, oops, this is my research. Okay. So this sum of xi, yi, I can actually figure it out like this. And this is sum of squares of x. So then it's about really typing these formulas in and finding a0, a1. I created a separate script that actually types in these precise values and uses and calls my linear regression of xy, and then I plot the data. So this is plotting actual data. This is plotting the model. So my model says, or the line is a0 plus a1x, and I can just do this in MATLAB to plot it. So let's see how this works. I have apparently a problem. Oh, I forgot to say hold on. Well, then let's try this again. Okay, so these are my points, and here is a line. Would you call this a good fit? Kind of. Yeah, I agree with that statement. It's kind of, for a linear fit, it's okay, but the point is that these points that I see, the cloud of points that I see, is not really well aligned with the line. Okay, it's actually probably some other functional relationship. And we're going to improve on that. But first thing that I want you to understand is that you're picking what are you fitting to. So I said fit a line, and the program fit the line the best as it could, except that line does not describe this data very well. Okay. So program that you write cannot fix that for you. You are the one to actually look at it and make the decision. But before this, we move on. Let's actually see what is the goodness of fit. So basically, I want to quantify the error. So is everybody good with this? Did you get here or close to here? Let's take a couple of minutes just to get closer. I think most of you wrote this code last time. If you did complete all of this, then basically go in slides further and try to quantify the error using so-called R square here. So this is basically, if I have two situations like this, I would like a number that would tell me, hey, you're in this situation, so you fit rather well, versus you're in this kind of a cloud-like situation, and you don't really fit this data well with line. Problem is, not much would fit this data well. There's not much correlation, but that's a whole different philosophical issue. We might want to do it anyway. So there are two numbers. One of them is basically normalizing this SR, this least sum SR that we were actually trying to minimize, and just like kind of normalizing it with respect of the number of points that I have. Okay. And instead of dividing by n, we divide by n minus 2, because two of these so-called degrees of freedom we're actually looking for. And the second one, more common one, is this coefficient of determination R2. And you can actually find it using these sums. So if you were done, basically go to the slides and add this to your code. So basically report on R square. Yes?
In the testing that we did, the code that we wrote, we used two x and y vectors. The x and y vectors to test the code that we wrote.
You have to. That's your data. It has x and y points.
Right. I'm just asking, what was the last number in the y vector?
Oh.
I didn't get all of it.
2.1. And slides are posted, by the way. There is a PDF on. Oh, the PDF. So I created this mid-class, but there's actually exercise, and it has all of those points on slide 18 in whatever I posted. So let's work on this a little more. So actually, let's compute this how good is my fit, this r and r square. You can compute both, but let's focus on adding r square. So I have my r as n times the sum of xy minus sum x times sum y. Oh, I need sum of y squares that I don't, so I'm gonna compute it, that I don't have. Bless you. This should be r, and then I'm gonna, r square is most common one to report, and I'm actually going to return that as a value here, r square. Now, the better your fit, the closer r square is to 1. So it's actually kind of measuring the degree of variation from the model. And the closer you are to 1, like 0.9 is very good fit. 0.5 not so much, so definitely below 0.6 or so is not a good fit. Good fits are typically between 0.8 and 1, let's say. Again, there's no strict rule, but I wouldn't really say that line describes data well if it's below 0.8. And 0.9 is great. So let's see what do we get here. I'm gonna report my R2. I'm gonna say goodness or R2 value for linear model fit is let's execute and see. How did it? What's going on? Don't see. So it's 0.76. I could have seen that it's not a very good fit. All right. Did you manage to type in R2 or R rather? Yes, square the R. We're not going into details why this is just a measure, but you can actually read up on it yourself. Good. Did everybody type it in to have less work to? All right. So just as a recap, basically what we are doing here is we are minimizing the sum of squared residual between the measured values and model. Okay. This model could be anything. Our initial model was a linear model. And in that case, I just have two parameters that define my line, and I'm looking for those two parameters. And the way I get them is to take partial derivative of this SR with respect to each of the parameters and just come up with linear equations to solve it. Great. That's actually relatively simple. And this is what we got in this case of linear models. So I actually have ready to go formulas for linear, so-called linear regression. Now, this relationship or the model does not always have to be linear, and actually we just saw a set of data that is not very well fit with the linear model. So you could actually have something nonlinear. Very simple thing could be, well, a parabola, right, which is my second order polynomial. So polynomials are not a big deal. Parabola is defined by three values. So I would go a0 plus a1x plus a2x squared. And then I would do partial derivative with respect to three of those, and I would get three equations and three unknowns. We know everything there is to know about solving linear systems in n unknowns if I want to define n of them. Okay? So sometimes you can actually do that, or you can modify a more complex nonlinear relationship to become linear. And one example like that would be this one. Let's say that I have this exponential relationship or a power law. Power law fits a lot of things. The joke is that if you haven't managed to fit your data with a power law, you haven't tried long enough. So essentially, a power law is a very common fit in complex data, especially data that changes over multiple scales of observation. So let's say, take a piece of paper. Okay. Take a piece of paper. And let's go with the second one just for kicks. So basically, if I'm assuming that my data, or the law that fits it well, is in the form of y is equal to a2 x to b2. So I'm looking for a2 and b2. I don't know what they are, but I'm assuming that that fits my data well. If I take log of this, okay, any log, it could be natural log, it could be log 10, it could be anything. Okay. So take a log of it and try to get this second relationship, and then tell me how would you use the code that you just developed to actually find these parameters. So I do need to know a little bit of something about logarithms. So whenever I have log of a product, it's a sum of log of individuals. This is log A2 plus log XB2. And I know that when I have a power, this is equal to B2. Do we agree? Yes? We're trying to get here. And can you now recognize a linear relationship? And what is this linear relationship between? And my data is now transformed by log. So if I take log of x and log of y, those logarithms are linearly related. So let's actually now try to, does everybody see that? So this is my new variable, if you will. You can call it uppercase y, y bar, whatever you want to call it. And this new variable from the data that I have, log of x. Okay. So those two, they appear to be linearly related. So I can find, this is now my A0, and this is my A1, if you will, from the linear regression. So let's see if we can find this better. So basically, whoops, try to plot this, fit this data, and I'm going to call it now A2, B2, just to refer to the slides. Okay. So you just have the code linear regression, so you can use it to solve the problem. And data is the same that we work with. And let's see whether this power law model fits the data better. And just to give you a hint, this is something that you should get. So this is basically the power law model fit. And indeed, its R2 is better. I'll flash the result. And let you and I know if we can help. This is using again the code that you have. Yes? Right. So if I take log of the data, and I have the data already, so I find the linear relationship. The code will spit out two. It will spit out this. This A0, this is A1. So I can find so I can use the code from log x and log y. Yeah. So to find A0 and O, but then I have to transform it to actually get into the sense of a little bit of algebra slash. Well, this whole logarithms, where do they fit? For me, it was called elementary mathematics. We had something basically that covered algebra, trigonometry, and blah blah blah. That was all elementary mathematics. So I don't know where do you put logarithms? How do you fit them? It's not calculus. I think it's algebra, but yeah. Anyway. Does everybody see? So the script, I hope you have the scripts. What is your x and y? So matrix dimensions must be that you don't have it. Yeah, you messed up.
That's what you say.
Number of well, x. See how many? So two number of elements in x. Oh, one. Well, that's very probably small y. So, one of them is missed. 7, 5.5, 4.5. Did you need one? No, okay. I thought that somebody made me. There. Maybe you didn't make me. Well, no, you have to do this. So now you need data. So let's fire up this. Log of it. And then I'm going to get some other I have to somehow back calculate what is A2. So basically, if I use my linear regression, let me cover this for everything. So if I use my linear regression, okay, on simply, instead of x and y, I give it log of x and log of y. And you can pick whether you want to do, this is a natural log in MATLAB. The base 10 log would be log 10, so just an FYI. So basically, I give it log x and log y. Then what I'm going to get out are A0 and A1, except that my A0 is now logarithm of A2, and I'm trying to find A2. Okay? So your logarithm of A2 is A0 the way this code thinks of A0, right? It's an intercept with the y-axis. So if my log of A2 is equal to A0, I can find out what A2 is, right? And my B2 is simply this A1 that is reported by a linear regression. Are we clear on that? So my linear regression is trying to fit a line to the data. This is my new y variable, and this is my new x variable, and they're linearly related. My intercept A0, what I called A0, is log of A2. So I can find what A2 is. Okay? And my slope, A1, is now B2. Well, so B2 is equal to A1, right? I'm still getting a lot of blank stares. Piece of paper. Let's write it down without a piece of paper. So this is my new variable. I'm going to call it y bar. And I'm going to call this x bar. Okay? And I'm going to call this as A0 and this is A1. So y bar is A0 plus A1x bar. Does everybody agree? Okay. So if I give my linear regression x bar and y bar as data, which is simply logarithm of the data that was coming in, logarithm of the data that is coming in. What my code will spit out is this A0 and this A1. Yes? I'm looking for A2 and B2, however, but I can see what I call log A2 is A0. So what is my A2 then? Algebra? Something? And my B2, well, is simply A is 1. What is the model that I actually begin with? How do I now plot my model data in my fit? My model is actually this. I just transformed it, solved it, transformed it back. So basically, I transformed my nonlinear problem into a linear problem after applying log, and then back. So let me quickly, so I'm going to redo this. I'm going to call this A0 and A1. Okay? And instead of x and y, I'm going to give it log of x and log of y. And my power model fit, so just give me a moment, is this. So let me just quickly execute it to see if I really improved in the... It's 0.95, so it's surely closer to 1. It's a better fit. Now I just want to plot it. So if I'm plotting x, what is my y according to the model? Okay. So it's A2 times x to the B2. I just have to recover, and I'm going to put a blue line. I'm just going to recover what is my A2 from here. A2 is exponential of A0, and B2 is A1. So my actual model is still y is equal to A2x to the B2. That's the power law model. Okay? We kind of, by transforming it with log, we transfitted it into the linear models, which I have the solution for. And then I just back calculated what A2 and B2 should be from this linear model. Let's see how it fits. And I'm going to have to do legend after this. And then power law. Okay, let's execute this. Somehow my data is now plotted in yellow. I don't know why. So this is my power law fit. And yes, it's a better fit. So my R2 value is 0.95. So it's a better fit to this data than is the linear relationship. I see that visually as well. Is the process clear? Not at all. Okay, so we're going to transform into the office hours mode. So please see me to basically re-explain this part. But the point is that I could modify a lot of different relationships, typically by taking either regular logarithm, natural logarithm, or maybe a little bit of algebra into a linear relationship between some versions of the data that originated inside.
How does the computer know what B2 or B1 is? So like we said that A1 is equal to B2.
So this is my intercept, which was A0, okay? And this is my slope, which was A1. In my linear model, I have intercept plus slope times x, mu x, right? So if I computed intercept and slope, which were A0 and A1 in my notation in the code, okay? Then basically log of A2 is this intercept A0, and slope B2 is equal to A1. A0 and A1 being names for intercept and slope in linear models.
So that's what I did. So the intercept of the power log and then that one.
Right, if I take the logarithm of this, then I actually have a linear relationship between log of the data.
But in your code, you said that B2 is equal to A1, right?
Yes, that was my slope. A1 is a slope. I took the linear regression of log of the data. So I fitted the log of the data. Let's plot simply log of x and log of y. Oh, I cleared everything. So this is my data. This is when I plot log of it against log of it. So it's kind of linear except for one outlier, right? So I can plot, like I can fit a line to this much better. Okay. I'm gonna turn off my